Hello everyone, welcome back to excellent series of lectures where we complete your entire course with respect to boards, JEE as well as NEET. So guys, this is Sagar Dalvi, your chemistry teacher, and I welcome you to this excellent series of lectures at Physics Wala. Well guys, we all are aware that in the previous session we started studying the organic chemistry and we begin with the first chapter, which is Haloalkanes and Haloarenes. And as I briefed you about this chapter, the first part of chapter we talk about the various mechanisms in detail. So that part we call it as reaction mechanism. So dear students, in our today's class, what exactly are we going to learn? Well, if you just try to think about what we have studied earlier, in our class number 1, we discussed about the introduction of different reaction mechanism that we have to learn. Well, in that we saw the first part of reaction mechanism that we'll have to understand is to learn about the different types of reagent. Then in detail we talked about the types of electrophiles and nucleophiles. Once that was done, we got introduced to different types of solvents, that is polar and non-polar. In polar also we further studied polar protic and polar aprotic solvents. Once that was done, we studied the impact of these solvents on the nucleophilicity of a nucleophile. So we had several characteristics of nucleophile, and at the end we also discussed about the leaving groups. So guys, in our today's class, let me show you what exactly are we going to learn. So in our today's class, we will be actually starting with the precise nucleophilic substitution mechanisms, that is unimolecular nucleophilic substitution, followed by bimolecular nucleophilic substitution reactions, and then we'll be talking about the neighboring group participation as well. So everyone, so if you just connect our previous chapter, a previous class, what we said is alkyl halide shows their characteristics reaction called as nucleophilic substitution and the elimination reactions, right? But nucleophilic substitution is a bigger term. Depending upon the nature of substrate, depending upon the nature of nucleophile, depending upon what solvent are we using for that reaction, that nucleophilic substitution reaction can be of further types. Those further types are what you see on your screen. That is unimolecular nucleophilic substitution reaction, bimolecular nucleophilic substitution reactions, neighboring group participation, and just like that there also exists something called as SNI, intramolecular nucleophilic substitution reactions, but we aren't covering that here. So to begin with, we will be studying today the first reaction mechanism, that is unimolecular nucleophilic substitution reaction. Okay guys, when you talk about this unimolecular nucleophilic substitution reactions, there are two important things that you should always remind to yourself. Firstly, when you see it is SN1, it's a unimolecular nucleophilic substitution reaction and it is a two-steps reaction. I want you guys to remember, first important point, SN1 is a two-steps reaction. Likewise, when we'll be learning SN2, remember SN2 will be a one-step reaction. So here SN1 is a two-steps reaction, and in that two steps, the first step is slow ionization of the carbon halogen bond, because of course we are learning this mechanism with respect to reactions of alkyl halide. So you will see there is going to be a carbon halogen bond. So in step number 1, slow ionization of carbon halogen bond results in the formation of carbocation. So this is another important term which I want you all to remember. You can call it as key feature of the reaction. Key feature as an important feature of the reaction. So SN1 is a two-steps reaction, and the key feature of this reaction is the formation of carbocation. So once the carbocation is formed, in the second step, whatever is a nucleophile, generally you will see solvent is going to act like a nucleophile, will attack at the carbocation and will result in the formation of corresponding product. Now in this SN1 type of reaction, when you talk about a nucleophile, we don't really take any stronger nucleophile like anionic nucleophile. Instead, the solvent which is used in the reaction mechanism itself acts like a nucleophile, and hence SN1 reactions sometimes are also referred as solvolysis. If solvent is used as a water, I mean if water is used as a solvent, then the same solvolysis reaction can also be referred as the hydrolysis process. So that's what we are mentioning here. Generally in this reaction, solvent itself acts as a nucleophile, and hence we also call this reaction as solvolysis. So guys, two important points that we'll have to remember. SN1 is a two steps reaction, and the first step, which is the key feature of this reaction, is a formation of a carbocation. In all SN1 mechanism, there will always be a formation of carbocation. And because we carry out this reaction in such a way that solvent itself is a nucleophile, we also call this reaction as solvolysis. So now, let us consider an example. If you see the example that we have taken is such that this is a chiral molecule. It is an optically active compound. And how do we know that? Well, in isomerism, precisely speaking, in optical isomerism, we have seen that if any organic compound contains only one chiral carbon, that is asymmetric carbon, then such compound will always be optically active. So when you look at this molecule, look at this carbon. The central carbon over here is a saturated carbon connected to four different groups: bromine, ethyl, methyl and phenyl. Such carbon, a saturated, a tetrahedral carbon to which all the four groups connected are different, we call it as chiral carbon atom. And if molecule contains only one chiral carbon, it will always be optically active. So what we have done is we have taken a chiral organic compound, which is of course an alkyl halide. Also, I want you guys to have a look at this structure, that this is a tertiary alkyl halide. The carbon to which halogen atom is connected, such carbon is connected to three more carbon atom directly, which makes such carbon atom as 3-degree carbon atom. So we call it as tertiary alkyl halide, and we are subjecting it to process of hydrolysis. So when you talk about the key feature, the important term or the important thing of this reaction mechanism is the formation of carbocation. Hence the substrate with which we are explaining this mechanism is such that when this will be forming its corresponding carbocation, it is going to be a stable carbocation. And that's why we have selected our substrate in such a way that once this undergoes step number 1 of formation of carbocation, this will form a relatively stable carbocation. Alright guys, now look, if you look at this substrate here, carbon and bromine, this bond is certainly going to be a polar covalent bond, because bromine being more electronegative, it will pull the bonding pair of electron toward itself, acquiring delta minus, and carbon will be acquiring a delta plus charge here, which makes this carbon electron deficient, isn't it? If this is electron deficient carbon, certainly water molecule would want to attack at this deficient carbon, because the oxygen atom in water is carrying a lone pairs, because of which it becomes nucleophilic in nature. However, the problem is when such nucleophilic water will try to attack at this deficient carbon atom, because this carbon is having 4 groups attached to it, this carbon is sterically hindered, or you can say it is crowded, because of which water will not be able to attack at this deficient carbon atom. So what happens in the step number 1? There is never attack of water takes place at this deficient carbon atom. But at the same time, the important characteristics of water molecule is, we all know the fact water belongs to category of a polar protic solvent, right guys? In the previous class, we discussed about polar solvents and non-polar solvents. So water being polar in nature and also having a high dielectric constant, it helps the dissociation of a carbon-bromine bond. So I use some new term here, polar protic solvent with a high dielectric constant. So what is dielectric constant? Well guys, now we are not getting into the details of that as much, but in simple words you can say dielectric constant is a physical quantity, or you can say a property of a solvent, which talks about how polar the solvent is, and in turn, I mean because of its polarity, how well it helps the dissociation of a bond to separate the species into ions. So more polar with a high dielectric solvent will have a ability to help the dissociation of a carbon halogen bond into separated ions. So because water being more polar and protic solvent, it will help dissociation of a carbon bromine bond. As a result of which, what happens here is, you will see this carbon bromine bond becomes polarized. So this is now in a process of breaking. So bromine will acquire delta minus, carbon will acquire delta plus, and other than that, the rest of the groups we are writing as it is. We have got ethyl here, methyl, and phenyl. Such a state of this molecule is where the carbon bromine bond is partial, will of course increase the energy of molecule because this is no more a permanent bond. So this carbon is now becoming more and more deficient, as a result of which the energy of molecule will increase. Such a state of a starting compound through which it has to always pass and get converted to a product which is having a highest energy content, we call it as transition state. I repeat one more time. Transition state is a state of a reactant through which it has to always pass in order to get converted to product, and it is a state of highest energy content. So because it is a state of highest energy content, what happens is immediately the carbon bromine bond breaks. Because carbon bromine bond breaks immediately, I will say now this step is a fast step. So here, this is the slow dissociation of a carbon bromine bond. So we are calling it as a slow step. And the slow step is experimentally determined rate determining step. So slowly carbon bromine bond became weaker and weaker. So it reached to the highest energy content state called as transition state. Immediately carbon bromine bond was broken, and as a result of which we get formation of a carbocation. So that's how we got formation of carbocation C2H5. Here we have got methyl group and the phenyl group with the carbon carrying positive charge on that. Right guys, this is what we have mentioned over here. It is a two steps reaction in which first step is a slow ionization of a carbon bromine bond, carbon halogen bond, resulting in the formation of a carbocation. So this first step where carbon bromine bond is in a process of breaking is a slow step, and hence it is a rate determining step. So guys, that was all about our step number 1. Now see what happens in step number 2. Once we get a stable carbocation, we must understand here the carbon is in sp2 hybridized state. Because carbon is in sp2 hybridized state, its geometry is going to be trigonal planar geometry. The moment it becomes trigonal planar geometry, now water molecule can attack at this deficient carbon atom, which was not possible earlier when it was a tertiary alkyl halide. Remember what we discussed? In the starting compound water, although nucleophilic, wasn't able to attack at the deficient carbon because of steric hindrance. So in step number 1, water never came into picture. So no nucleophile in step 1. The carbon bromine bond dissociates to form a carbocation and the Br minus ion to give you a corresponding carbocation. This carbocation once formed now can undergo attack from a water molecule. So everyone here, a water can attack at this deficient carbon from the same side from where the bromine has left. So the side from where bromine has left, you can call it as front side attack. So this is the front attack. Or water can attack at the deficient carbon from the side opposite to that of from where the leaving group, that is bromine, has left. You can call it as backside attack. Everyone, please understand, look at the previous slide. So if I assume that front side where bromine was present from where bromine has left, so I will say The attack of water from the same side from where bromine has left, you can consider it to be front side. And if the attack takes place from the side opposite to that of from where bromine has left, you call it as a backside attack. Now, when the front side attack takes place at this carbon, of course followed by deprotonation, because when water will attack at this deficient carbon, oxygen will acquire a positive charge. So it will immediately undergoes deprotonation, meaning effectively it is not water will be attached to cationic carbon, but the OH group eventually will be attached to this carbon. So the product obtained can be represented like this. With respect to the way we have represented the two-dimensional structure, I'm putting in the same way. And then later we'll also see in 3-dimension. So let's assume bromine had left from here. So instead of that, now we have got OH. Rest of the group as it is, we had ethyl here, methyl here, and the phenyl group here. And if I assume the attack of water taking place from the side opposite to that of bromine, then the presence of OH will be represented like this. And these are the remaining groups. C2H5, that's pH. And this is methyl. Right, everyone? Well, now I want you guys to look at the structures and compare them with the starting compound. In the starting compound, when we had a tertiary alkyl halide, instead of OH, we had a bromine. Which means if I compare this structure with the starting compound, I can see in place of bromine, I have got OH. Rest of the configuration is similar to the starting compound. Hence, when you get such product whose configuration is similar to that of your starting compound, we say the product is obtained with retention of configuration. So the configuration in the product is being retained as that of your starting compound. Whereas here, the position of OH group is exactly on the opposite side of that of where the bromine was present. So I will say this product is obtained with the inversion of configuration. The configuration seems to be inverted in the final product, which means in SN1 mechanism, step 1 is a slow dissociation of a carbon halogen bond to results in the formation of a carbocation, which is the slow step, rate determining step. Once the carbocation is formed, because carbocation is planar in nature, attack of water molecule can take place from either from the front side or from the back side. As of now, it seems like these two attacks are equally probable because this is the planar structure. If as of now I am saying that these two attacks are equally probable, which means the retention of configuration and inversion of configuration of the product should be obtained in equal proportion. When such two products are obtained in equal proportion, and if both of them are chiral molecule, then I must say the product obtained is a racemic mixture, and hence this process can also be called as racemization. Right, guys? So what we have learned is optical activity in stereoisomerism, that is optical isomerism, is there's a term called as racemic mixture. It is the mixture of equimolar amount of dextro and levo isomer of the same compound, right? So here I have got two isomers of the same compound which are optically active, and we are considering that the attack is equally probable and hence both must be obtained in equal amount. So I can say that this is a racemic mixture. However, the fact is the product that you get is never a perfect racemic mixture. Rather, the product which we get, we call it as partial racemic mixture, and the process is called as partial racemization. Well, guys, I'm going to explain it to you that in detail. Why do we call it as partial racemization and not the complete racemization? But before that, I want you guys also to understand one very important feature of this solvent, which itself is acting like a nucleophile. Look, in SN1 reaction, when we take water as a solvent, first important role of this solvent is, because it is polar solvent with high dielectric constant, it helps dissociation of a carbon-bromine bond, which results in the formation of carbocation along with bromide ion, which is our leaving group, rather a good leaving group. Now, after formation of carbocation and this anion, because our solvent is water, this water also stabilizes this carbocation. We are aware that water is polar, it is dipole. So the negative pole of water, that is oxygen, can attract this positively charged cation, and hence carbocation can be stabilized by ion dipole interaction. And formation of carbocation, as we have studied, is the key feature of this reaction mechanism. Hence, the role of polar solvent is very, very important in this SN1 reaction mechanism. So, polar protic solvent with high dielectric constant does not just helps us to form a carbocation, but even after formation of carbocation, it is being stabilized by such solvent. Hence, use of polar protic solvent in SN1 type of mechanism is very, very important. So we have to select our solvent wisely. So guys, that was step number 1. This was step number 2. Let's understand step number 2 in detail now. Okay, everyone, let's have a look at this. Well, so now we are taking structure in 3 dimensions. So to make you guys familiar with 3-dimensional structure, let me show you how our starting compound was. Well, so we had our starting compound, which is I'll write it down here. Hold on. Okay. Let's say this is ethyl. This one is methyl. Here we have got phenyl group. And here we have got bromine. That was our starting compound, right, everyone? So due to electronegative difference between carbon and bromine, this bond was anyways polar, which eventually broke to give you carbocation, which is like this. Now, because this carbocation is planar, we have represented its geometry like this. Okay. So ethyl group is in the plane of paper. Phenyl group is coming outside the plane of paper. Methyl is going inside the plane of paper. Now see, like what we said, the side where bromine is present, we consider it to be a front side. And opposite to that, we call it as back side. So when bromine left from here, we got a carbocation, and water is attacking at this carbocation. If from the same side where bromine was present, we call it as front side. Hence, this is called as a front side attack. Let's call it as path A attack. And then there is a back side attack. Let's call it as path B attack. As of now, the detailed mechanism of step number 2, we are explaining with the help of front side attack. The similar can be considered for the backside attack as well. So look, when water is attacking from the front side, you will see there will be new bond making between oxygen and carbon, which we are representing by a partial bond, where oxygen is now in a process of forming bond with the carbon. Because there is a partial bonding over here, of course, the energy content of this state is again going to be very high. Such a state of high energy content through which every reactant has to pass in order to get converted to product is what we call it as transition state. Hence, I'll call it as transition state. But because in step number 1, we already have got a transition state 1, I'm referring this as transition state 2. Because it is transition state, the next step, of course, it is going to be a fast step. So what will happen in this fast step? There will be permanent bond formation between carbon and oxygen. Do you see that here? As a result of which, now oxygen will carry a positive charge, because originally oxygen had 2 lone pair, one of which is used to form a bond here. So oxygen is now left with only 1 lone pair and a positive charge on it. Naturally, when there is a positive charge present on oxygen, in order to acquire the neutrality, this will immediately undergo deprotonation, meaning now one of the OH bond will be in a process of breaking. So you'll see we have represented one of the oxygen hydrogen bond as a partial bond. Again, the moment you represent partial bond, this is also state of higher energy content. Hence, we'll refer this as transition state 3, which eventually undergo a loss of proton from here. So the step can also be regarded as a deprotonation step. Upon deprotonation, we got the product here. So if you compare the starting compound and the final product as a result of attack from the front side, you will see the incoming group OH is exactly on the same place where the bromine was present. Hence, the product obtained will be said to be having retention of configuration. Right, everyone? So exactly in the similar fashion, imagine if the attack of water would have been from the back side, what would have happened? We would have got the product where OH, instead of to the right, we would have mentioned to the left in this structure, which means we would have got exactly the mirror image of this, isn't it or not? Right? Imagine water would have attacked from here, then these two groups would have been flipped to the right, OH eventually would have been to the left here. So the product in that case which we would have got from the backside attack will be the one having configuration inverse of this, opposite of this. Hence that product would have been called as the product with inversion of configuration. Now everyone, when we look at this attack of water, it appears like attack of water, the deficient carbon is equally probable from the front side and from the back side. Hence the product with retention of configuration and inversion, which we have not shown because it is going to be exactly similar to that, just that from opposite side. Those two products should be obtained in equal amount. However, in reality, we don't get complete racemization, we get partial racemization. And why it happens so? Well, not to forget, when the carbocation formation took place, the bromine left from the front side, right? The bromine left, let's say, from the front side, meaning imagine from here the bromine has left. When bromine leaves and the carbocation formation takes place, even after dissociation of carbon and bromine, this is still a cationic carbon, which you can see here, and bromine has left in the form of Br minus. So because these two are still oppositely charged ions, although Br has left, it will still remain in the vicinity of this compound on the front side because those are oppositely charged species. Hence, to some extent, the front side is hindered or blocked for water to attack comfortably. Hence, water preferably attacks from the back side. When the attack from the back side is prominent or more than that of front side, the product with the inversion of configuration obtained will be more than the retention of configuration. Hence, we say in case of SN1 reaction mechanism, the product obtained is a partial racemization which has more attack from the back side than that of front side. So guys, that is about the stereochemistry of the product obtained. Now let us talk about some important characteristics feature of this SN1 reaction mechanism. Guys, I'm hoping that you all are understanding what we are doing. We are going very slowly, making sure that every small point is conveyed to you all. So let us talk about the rate expression. Well, so the rate expression for this reaction, looking at the reaction mechanism, can be written as rate of this reaction is equal to K constant into molar concentration of only substrate. So if you just recall the rate determining step over here, in rate determining step only substrate is involved, no contribution of a nucleophile, that is solvent. Hence rate is directly proportional to molar concentration of substrate only. Meaning, in other words, you can say rate is equal to K into molar concentration of substrate. Now guys, what is the significance of this? This tells you that rate of SN1 reaction can be altered by changing the concentration of substrate, but changing the concentration of nucleophile, that is solvent, will have no impact on the rate of the reaction. For example, if I double the concentration of substrate, the rate of SN1 reaction will also be doubled. If I triple the concentration of substrate, the rate of SN1 reaction will also be tripled. But change in the concentration of nucleophile, meaning whether you double the concentration of nucleophile or triple it, it will have no impact on the rate of SN1 reaction, because rate expression is telling you that rate is equal to molar concentration of only substrate. Alright everyone. Second important Characteristics about molecularity and order of reaction. Well, rate expression was showing us that in RDS only one molecule is involved, that is substrate, and hence we will say the molecularity of reaction is 1. So we just look for how many molecules are participating in RDS, that tells us about the molecularity. So molecularity is 1, and rate expression will tell you rate is equal to K into molar concentration of substrate. So nothing is written, meaning substrate to the power 1. That indicates the order of reaction is also 1. So molecularity and order of reaction, you can say it is unimolecular. And first order reaction. Alright everyone, and then partial racemization. Well, I have explained it earlier, but just to have a record of it, you can see on your screen. Since the diffused leaving group, meaning in this example we are talking about bromide ion, has left from the front side, being anionic, the Br minus which has left is anionic, it remains in the vicinity of carbocation as an ion pair, because carbocation is positively charged ion, Br minus is negatively charged. As a result of which it blocks the attack of the incoming nucleophile, that is water, from the front side. Hence the preferred attack of nucleophile takes place from the back side with more inversion of configuration than the retention of configuration. Hence the general term that we use here is that it is the partial racemization. But remember, in the partial racemization, the contribution of inverted product is always going to be more than the retention of configuration product, and this is experimentally supported. Alright everyone. Well, other than this, the next important point that we remember is energy profile diagram. Well, as of now, one difference you'll find in this energy profile diagram in our reaction mechanism is, in our reaction mechanism we have got 3 transition states, but here we have got only 2 transition states. Why it is so, I will explain it to you. Firstly, let us understand what is energy profile diagram. Well, dear student, the name itself suggests that it is the diagram, or it is a diagrammatic representation of energy changes taking place right from the reactant up to the product. Meaning, as your reactants changes into product, what is happening to the changes in the energies of all those reactants, intermediates and product, when you express them in terms of a graphical representation, you call it as energy profile diagram. Well, so guys, what we had right in the beginning, we had a substrate here, right? So this is the substrate. If you just go back and try to recall the reaction, what happened? You had a substrate. That substrate, in presence of polar protic solvent, initially undergone slow dissociation of a carbon halogen bond. So when the bond was partial, we got formation of transition state 1, right, in a rate determining step. So as the reaction progressed, slowly the substrate got converted to transition state, which is the state of highest energy content. That's why, as you can see, on x-axis there is a progress of reaction, on y-axis there is energy. So as the reaction progressed, your substrate slowly got converted to transition state. So this is the transition state 1, a state of maximum energy content, right? Then what happens? Immediately carbon bromine bond dissociated, and this got converted to carbocation. Now, because the carbocation form is tertiary, this is 3 degree in nature, we know from general organic chemistry, tertiary carbocatans are more stable than secondary than primary. Because tertiary carbocation is stable, meaning its energy will decrease. Also, the carbocation which is formed is surrounded by several water molecules via ion dipole interaction, which was important feature of solvent selection, right? So, with the stability of carbocation, its energy has decreased. Hence, from transition state, the energy decreased as the reaction progressed, and we got a point where it is representing a carbocation. Once carbocation is formed, now listen to me carefully. We had shown attack of water. So when we showed attack of water, there was new bond formation between cationic carbon and oxygen, which was a partial bond. So partial bond meaning again it got converted to transition state 2. Now the only difference is here we have directly represented a nucleophile, meaning instead of water, imagine if I would have represented only OH minus, then there would have been a process of bond making between the carbon and OH, and you would have got transition state 2. But once this bond permanently forms, carbon became again tetravalent and it will form a stable product. And because in nucleophilic substitution reaction, products are more stable than reactant, the energy of product form is lesser than that of the reactant. Hence, you will be getting only 2 humps corresponding to 2 transition state. When we consider our reaction mechanism, we have taken water. Because we have taken water, we got third transition state as well. Why? Because it was not anionic species, it was neutral. So when water attacked, you got transition state 2. When oxygen and carbon bond became permanent, you got CO bond which is permanent, but then it had to undergo deprotonation. From OH2, it had to undergo deprotonation. Let me show you that. And for this deprotonation, we got this extra transition state. Imagine instead of water, if the attack would have been only from OH, you would have directly got this as the product after transition state 2. Right everyone? Imagine if you would have had got only OH. So OH would have attacked, partial bond transition state 2. Once this is permanently formed, you would have got product. So depending upon what nucleophile is given, you have to mention that. So with respect to your NCERT, you consider SN1 reaction mechanism. Because we are considering 1 carbocation and 2 transition state, you will be getting 2 humps here, 2 peaks you can say. So guys, when the reactants and the products are plotted against, or you can say when energy of reactants and product is plotted against the progress of reaction, the curve obtained is what you call it as energy profile diagram. So this is the energy profile diagram for SN1 reaction mechanism. Well guys, we have studied a lot till now. Let me just summarize what we have seen so far. We started our discussion with nucleophilic substitution reaction mechanism. Like we said, depending upon the nature of substrate, solvent and nucleophile, there are several types of nucleophilic substitution mechanism exist. We started with the first type called SN1. 2 important points that we remembered. SN1 is a 2 steps reaction. And the key feature of this SN1 is formation of carbocation. So it involves step number 1 where slow dissociation of a carbon and leaving group bond takes place to form a carbocation. In step number 2, nucleophile, generally which is solvent itself, attack at the carbocation from the front as well as from the back side, whereas attack from the back side is prominent and hence you get the partial racemic mixture. Well, with respect to that, we draw energy profile diagram and we study some important characteristics, one of which is rate expression. So because in rate determining step, we can see only substrate is present, rate is directly proportional to molar concentration of only substrate. So changing the concentration of substrate will also alter the rate of reaction, but changing the concentration of nucleophile will have no impact on the rate expression. Right everyone? Okay, now proceeding further with the factors affecting the rate of SN1. Well, why I have been emphasizing on, remember the key feature, that is formation of carbocation, because that is what is going to help us now to decide the factor. The first factor is the nature of substrate. Well everyone, let's say if I have got a molecule where that is a primary carbon, because a carbon directly connected to only one carbon, I'm putting halogen here. So this is primary alkyl halide. Now let's say a carbon which is carrying halogen had only one alkyl. Now I'm putting 2 alkyl groups at the carbon carrying halogen. This is secondary alkyl halide. And now a carbon carrying 3 alkyl group is carrying halogen. So this is tertiary alkyl halide. Now, if I've got 3 different types of alkyl halide acting like a substrate, and if I have to decide who's going to react towards SN1 at a faster rate and who's going to react at a slower rate, then I will always think about rate determining step. In rate determining step, the product obtained is a carbocation. So whichever carbocation is going to be more stable, the rate of reaction towards that alkyl halide will be certainly faster. So I will have to assume if the carbon halogen bond is broken, what carbocation I'm going to get? Tertiary. Tertiary carbocation being more stable, it will undergo SN1 reaction faster than secondary alkyl halide, than primary alkyl halide. Hence I can say, as the number of alkyl group on the carbon carrying leaving group increases from 1 to 2 to 3, rate of SN1 reaction also increases. As the number of alkyl groups on the carbon carrying leaving group increases, the rate of SN1 also increases. That's the nature of substrate. Nature of leaving group? Well, because we want carbocation formation to take place, we will always prefer to have a good leaving group, because good leaving group is the one which will depart the substrate faster and will help formation of carbocation at a faster rate. Hence, you can say better leaving group always favors the rate of SN1, and this condition is going to be universal condition for all the mechanism, whether they are substitution mechanism or whether they are elimination reaction mechanism. So guys, here let's say if I have got alkyl fluoride, comparing that with alkyl chlorides, comparing that with alkyl bromides, and finally with alkyl iodide, what we all know is poor bases are good leaving group. So HI is stronger acid, and stronger acids conjugate base is poor. So I minus is a poor base, and poor bases are good leaving group, which means the rate of SN1 will be fastest when iodide is the leaving group, if I consider halides as the leaving group. So iodide will give you SN1 fastest, then bromide, then chloride, and the slowest reaction rate would be in case of fluorides. Third factor is about the nature of solvent. Well, having said earlier, we want a polar protic solvent with a high dielectric constant, which helps dissociation of a carbon halogen bond, because key feature is formation of carbocation. So any solvent that will help formation of carbocation will always support SN1. And not only that, once the carbocation is formed, it has to be stabilized. So polar solvent stabilizes the carbocation via ion dipole interaction. Hence everyone, polar protic solvent with high dielectric constant helps dissociation of CX bond, that is formation of carbocation. So polar protic solvent will favor SN1. Nature of nucleophile. Whenever you talk about nature of nucleophile, I want you all to think about rate expression. In rate expression, we mentioned that R is directly proportional to molar concentration of substrate only. There was no nucleophile, meaning the concentration of nucleophile does not really have any impact on the rate of reaction. However, we have seen that the solvent itself, water itself, was acting like a nucleophile. Hence the process we call it as solvolysis. So solvent itself is going to act like a nucleophile. So if your solvent is water, water is a neutral molecule, and we know the fact anionic nucleophiles are stronger than its neutral molecule, right? Yesterday we saw characteristics of nucleophile. OH minus is stronger nucleophile than water. So if water is used as a nucleophile, in other words, you can also say that we need a poor nucleophile for SN1 reaction to take place. Those poor or weak nucleophile are nothing but solvent itself. That was the nature of nucleophile. Well guys, the important feature of SN1 have been done. Now we are going to study some more substrate which shows SN1 reaction other than primary, secondary and tertiary alkyl halide. So there are some typical substrate which also favors SN1 reaction mechanism to take place. So getting introduced to some more extra nucleophilic substitution substrate. First one is allyl halide. Do you see that here, everyone? Now this allyl halide is also favored by SN1 reaction mechanism, because in SN1 reaction mechanism, key feature is formation of carbocation. So imagine if carbon halogen bond breaks, if you get this carbocation, the allyl carbocation which is formed. What is allyl carbon, everyone? A carbon which is itself sp3 connected to sp2 carbon is called as allylic carbon. Since a halogen atom is attached here, I'll call this as allyl halide. Now why is this favorable towards SN1? Because in SN1, first step is slow dissociation of a carbon halogen bond forming a carbocation. The carbocation form is such where the pi bond is in conjugation with this vacant orbital. So a pi bond can delocalize towards vacant orbital. Hence this allyl carbocation is stabilized by phenomena of resonance. More stable the carbocation, faster will be the rate of formation of that carbocation. Hence allyl halide will be favored towards SN1 mechanism. Similarly, let's talk about benzyl halide. Now what is benzyl halide? A carbon which itself is sp3 connected to sp2 carbon of a benzene is called as benzylic carbon. Because halogen atom is connected to benzylic carbon, we call it as benzyl halide. Now here as well, if you take this in presence of polar protic solvent, step 1 will be slow dissociation of a carbon halogen bond resulting in the formation of carbocation, which we'll now call it as benzylic carbocation. Now benzylic carbocation is such where the vacant orbital of this cationic carbon is in conjugation with the pi bond of the ring. So pi in conjugation with vacant, or what you call pi alternate vacant orbital, it will delocalize here. So you'll get formation of double bond here, but this carbon would be deficient. Again this deficient carbon will be in conjugation with the pi bond, so this can delocalize further and the conjugation will be extended like that. As the conjugation will be extended, the stability of carbocation will be even more stable the carbocation, faster the rate of SN1. Hence benzyl carbocation undergoes SN1 reaction. And then finally, imagine if we have got alkoxy group at the carbon carrying leaving group. Alkoxy, RO meaning alkyl and oxy meaning alkoxy group at the carbon carrying leaving group. If you subject it to SN1, a carbon halogen bond would be broken. So this carbon would be carrying a positive charge. Now the carbocation form is such where a vacant orbital is in conjugation with the heteroatom carrying lone pair, which is the perfect condition for back bonding. So the lone pair of heteroatom will delocalize completely into vacant orbital, satisfying the octet of this carbon, hence stabilizing it. So now you can see over here, the carbocation which is obtained is stabilized by back bonding, meaning it is even more stable than the previous two. And more stable the carbocation, faster the rate of SN1. That's how this allyl halide, benzyl halide and alkoxy at the carbon carrying leaving group are the substrate which favors SN1 reaction mechanism. And likewise, there are some substrate which are completely non-reactive towards SN1 reaction mechanism. Those substrate which are non-reactive, you can call them as inert substrate towards SN1. First one is vinyl halide. Look at this, everyone. What is vinylic carbon? The carbon which itself is sp2 is called as vinylic carbon. So imagine you had ethene. You substituted one H with the halogen, so you got vinyl halide. Now, because the key feature of SN1 is formation of carbocation, let us say hypothetically we assume that the carbon halogen bond is being broken. So this vinylic carbon will carry positive charge. So this is vinyl carbocation. But we have studied that the positive charge at the doubly bonded carbon is highly unstable. So the vinyl carbocation which is formed is not stable. So because this is not stable, this will not be formed. If carbocation cannot be formed, the substrate cannot undergo SN1 type of reaction mechanism. Hence, vinyl halide is non-reactive towards SN1. Similarly, this is phenyl halide. Halogen is directly connected to the carbon of benzene. So this is phenyl halide. If we consider carbon halogen bond is breaking, resulting in the formation of phenyl carbocation, you will see again the positive charge is at the doubly bonded carbon. Such carbocations are not stable. Because they are not stable, they will not undergo SN1 type of reaction mechanism. Likewise, the third substrate that we have over here, everyone see this carefully. I have got some bicyclic compound. In bicyclic compound, the two common carbon where the three bridges are connected, you call it as bridgehead carbon. So now we have got halogen, meaning leaving group present at the bridgehead carbon. So if I hypothetically assume the carbon halogen bond breaks and you get a carbocation, so the cationic carbon, meaning the positive charge at the bridgehead carbon, is never stable. Why so? Because if there is a positive charge at the bridgehead carbon with only 3 sigma bond, meaning the carbon atom is in sp2 hybridized state. sp2 hybridized carbon will always demand geometry to be linear and in cyclic structure with especially lesser than 8 carbon atom. The planarity cannot be achieved. Hence, such carbocation at the bridgehead carbon is highly unstable because vinyl halide, phenyl halide, halogen at the bridgehead carbon forms their corresponding carbocation which are highly unstable. Such substrate will not undergo unimolecular nucleophilic substitution reaction. So dear students, that was all about SN1 type of mechanism. Now that we are done with SN1 type of mechanism, we are all set to learn the second mechanism, that is SN2, bimolecular nucleophilic substitution reactions. Guys, we will be doing SN2 very soon. I'm just taking short break to drink some water. You guys can go through the introduction till then. Okay, everyone. So the second mechanism that we have to learn for today is about SN2. You call it as bimolecular nucleophilic substitution reaction. By now, we must have understood that when I'm calling it as bimolecular, which means it is talking about the molecularity of reaction. Yes. So molecularity of this reaction is going to be 2. Hence, you call it as bimolecular. Now, let us learn this in a similar pattern that we learn SN1. First of all, we understood that SN1 is a two-step reaction mechanism. Similarly, SN2 is a one-step reaction mechanism. So it's a single-step reaction. Secondly, the key feature of SN1 reaction mechanism was formation of carbocation. Here the key feature is SN2 reaction is concerted reaction mechanism. When I say a term concerted, meaning when the breaking of a bond and the making of a new bond takes place simultaneously. Bond making and bond breaking takes place simultaneously. You call it as a concerted step. Okay. So 2 important points. SN2 is just one step reaction and it's a concerted step. Concerted meaning bond breaking and bond making takes place simultaneously. So guys, SN2 is a single step reaction. Hence, where the bond breaking and new bond making takes place simultaneously, we call it as a concerted reaction. So to understand, let's take example. Everyone, once again, if you observe the substrate that we have taken such a alkyl halide where the carbon carrying leaving group is connected to all the 4 different groups, isn't it? So even this is a chiral substrate. Yes, we all are aware that this is a chiral substrate, but very carefully the valencies of that chiral carbon atom have been satisfied by the small size atoms or a group of atoms. Recall what we had in case of SN1. We had a carbon containing three bulky substituent. We had ethyl, we had methyl, we had a phenyl as well. So that was bulky or sterically hindered carbon atom. It was more substituted carbon. Hence the carbocation form was stable. Now the carbon carrying leaving group is connected to smaller group. Only one methyl is relatively bulky, but rest of the two valencies are satisfied by the small size atom, that is hydrogen and deuterium. Then we allowed it to react with OH minus ions. So now guys, you can see the difference. In case of SN1, we had a solvent itself acting like a nucleophile. Here we have anionic nucleophile. So basically what we are trying to understand over here is, here we have strong nucleophile. We have studied this in class number 1 that anionic nucleophiles are stronger than its corresponding neutral molecules. So for SN2 we have less sterically hindered carbon carrying leaving group and anionic meaning strong nucleophile. So let's say this OH minus substitutes the Br and you get formation of an alcohol with the loss of Br minus. This is a simple reaction representing SN2 reaction mechanism at the chiral center. Let us understand the same reaction in 3 dimensions in detail. So let's say we have the same substrate represented in 3 dimensions. So these 2 bonds which are represented by the normal lines are the bonds in the plane of paper. This is called as solid line or solid wedge, you can say. A bond coming outside the plane of paper, and this is the hatch wedge or dashed line sometimes people call. This is the bond indicating a group going inside the plane of paper or behind the plane of paper. Now the carbon having a leaving group bromine and the side where leaving group is present, let's call it as front side. So this is front side. And side opposite to that we are calling it as back side. Okay. Now because carbon is connected to bromine, bromine is more electronegative, so acquiring delta minus, carbon is carrying delta plus charge. Now at this delta plus charge, the nucleophile OH minus will try to attack, but there's a possibility that OH minus can approach this carbon atom from the front side as well. But the front side attack of OH at this deficient carbon is not possible. And why so? Imagine when OH minus ions are approaching at this deficient carbon atom from the front side, where there is already electronegative atom carrying 3 lone pair is present. So when the OH minus will try to approach the deficient carbon from the front side, it will firstly experience inter-electronic repulsion because nucleophile themselves are electron rich and the leaving group is also carrying 3 lone pair. Secondly, the front side is substituted by a relatively larger size halogen atom which will not allow nucleophile to approach from the front side. Hence the attack of nucleophile at the deficient carbon takes place from the back side. Why is this backside attack possible? Is because firstly there is no steric hindrance because the groups present at this carbon atom are small size group, which was not the case in SN1. Secondly, there is no atom present which is carrying a lone pair like Br is carrying, so that there will be no inter-electronic repulsion for OH to approach the carbon. Hence, in case of SN2 mechanism, the attack of nucleophile takes place at the deficient carbon from the back side. So you can see here, this is a backside attack. So as a result of backside attack of OH at the carbon, this is found to be the slow step, and because it is a slow step, it is found to be a rate determining step. See now what happens? Here bond breaking and bond making is taking place simultaneously. Hence we are referring this as concerted step. So you will see a state will be achieved where there will be a partial bonding between carbon and bromine and partial bonding between oxygen and carbon as well. But the difference will be carbon-bromine bond will be in a process of breaking and carbon-oxygen bond will be in a process of making. So you can say for a moment the carbon is going to be pentavalent. So if I draw such pentavalent carbon, it can be represented like this. So we have got H here, this is deuterium, and this is methyl. Please understand, as of now, these three bonds are in one plane. Hydrogen in the plane of paper in the same plane, D is coming outside in the same plane, methyl is going behind the plane of paper. And carbon-bromine bond is now a partial bond. And here we have got carbon-oxygen bond of OH, which is also a partial bond. It's just that carbon-bromine bond is in a process of breaking, so this is delta minus. Oxygen-carbon bond is in a process of breaking, so even here we have got delta minus, and here we have got delta plus. This is a temporary state of a molecule where carbon is pentavalent. Hence, the energy of this molecule will be very high. Such a highest energy state of molecule is what we call it as transition state. And once transition state is formed, it immediately will undergo dissociation of carbon-bromine bond. So carbon-bromine bond will now break. Hence, the step is going to be a fast step. So if bromine is left from here, a carbon-oxygen bond will become permanent bond and the carbon will become tetrahedral. So we have got carbon. See, now once Br has left, these two bonds will flip little to the right. This OH will come down because the carbon is going to be tetrahedral and the tetrahedral geometry will always have a bond angle of 109.5. So keeping that geometry in mind, after departure of Br minus, the product obtained can be represented like this. That's H. Solid line was always a deuterium. Hatch wedge was methyl. And this is the new bond formed between the hydroxyl group and the carbon atom. So that's our product. And what has left? Br minus has left as a leaving group. So we have got Br minus. Guys, if you observe the product which we have got over here, and if you compare the configuration of starting compound, the only difference you will see, instead of Br, now we have got OH, right? But imagine if I keep OH over here and compare the geometry of starting compound in the product, wouldn't these two be mirror image of each other? I'm saying if I consider OH here and then if I compare the geometry of starting compound with the product, wouldn't these two geometries would be mirror image of each other? Yes, they would be, which means the product which is obtained has a configuration exactly inverted to that of the starting compound. Hence, the product obtained will be said to be having inversion of configuration. So this is inversion of configuration. Now everyone, here there is no possibility of front side attack because it's a concerted step and incoming nucleophile can only manage to attack from the back side. So all the concentration of OH who's attacking at the carbon will always be from the back side, meaning the entire product obtained will always be having inversion of configuration. Hence we say the product is obtained with 100% inversion. This 100% inversion is also referred as Walden inversion. So everyone, one very important feature we have to understand is that in SN2 reaction mechanism, the entire product obtained will always have inversion of configuration. That 100% inversion of configuration is referred as Walden inversion. And what is the factor responsible for 100% Walden inversion? Is the backside attack of an incoming nucleophile. Alright everyone. Okay. So now this is your entire reaction mechanism, and let's try and understand the characteristics of this SN2 reaction mechanism. First one, backside attack. Well, so the backside attack of incoming nucleophile at the deficient carbon in a concerted step will result in the formation of inversion of configuration. So we can just note it down. Backside attack of a nucleophile results in the formation of product with 100% inversion called Walden inversion. Okay guys, now with respect to this reaction, there is one very famous question that they generally ask is, look, suppose if I tell you that this is the compound having some particular, you can say optical rotation. Let's say I'm saying the starting compound is a dextro-rotated compound. It's a D isomer. Okay. And you carried out SN2 reaction mechanism and this compound got converted to some alcohol. So what is going to be the stereochemistry of this product? Where one of the option will be levorotatory product. Is that going to be our product or is that going to be our answer, everyone? Well, so because our starting compound is dextrorotatory and we know the fact the product obtained will be with 100% inversion, we always feel that the product obtained will be a levorotatory compound. But guys, let me tell you one very important thing. Dextroisomer and levoisomer is the term which is related to the enantiomers, meaning they are the optical isomers of the same compound. So for me to be able to say that a dextrorotatory compound is converted to levorotatory compound, first of all, these two products or these two isomer has to be of the same compound. And let me tell you, this is alkyl halide and this is alcohol. These two are not at all same compound. If they are not at all the same compound, how can I say one is dextro, other is levo? Well, so what kind of compound is that? Whether dextro or levo, you will have to experimentally find out whether it is dextrorotatory or levorotatory. Just because this is dextro, you cannot say this is levo because this is a new compound altogether. This is alkyl halide, this is alcohol. So whether this is dextro or levo will be an experimental fact that we will have to find out. We cannot tell whether this is dextro or levo. We can only say that this is one of the optical isomer. This is one of the stereo isomer because even this has one chiral carbon. And compound having one chiral carbon will be always optically active. However, let us say if someone tells us this is R isomer, capital R. Okay, this is capital R. Then whether or not this will be capital S, can we tell that? Yes, we can tell that. Why? Because if you look at the starting compound, bromine is the highest priority group which is being substituted by OH, and in the product we have the OH group which is also the highest priority group, meaning a highest priority group is being substituted by a highest priority group only. And now if there is inversion, then I can say that if this is capital R, then the product obtained can be capital S because there is an inversion which has taken place. So R have been converted to S. That too, you will only be able to tell if the priority of group which is replaced and the priority of group who has replaced are identical. But about dextro and levo, we cannot comment about that. I can only say that this is one of the stereoisomer. Well, just a point that I had to discuss. Coming back to the characteristics, rate expression. Well, from the reaction mechanism, we can see rate is equal to K into. If you go back to reaction mechanism step here. So rate determining step has involved both substrate as well as nucleophile. Because both substrate as well as nucleophile are involved, you can say it is bimolecular reaction, meaning rate of reaction is proportional to molar concentration of substrate as well as nucleophile. So rate is equal to K into product of molar concentration of substrate and the nucleophile, which means if I change the concentration of substrate, the rate will change. Also, if I change the concentration of nucleophile, the rate will also change. So for example, if I double the concentration of substrate only, the rate of reaction will double. If I double the concentration of nucleophile only, keeping substrate same, the rate will also be double. If I double the concentration of substrate as well as the concentration of nucleophile will also double, then the rate will quadruple. The rate will become 4 times of what is originally present. Similarly, if you can say, let's say if I decrease the concentration of substrate by half, then the rate of reaction will also be half. So if you change the concentration of either of this, it is going to alter the rate of reaction. All right, guys. Well, so since 2 reacting species are involved in RDS, we know that the molecularity of reaction is 2. This is what I have explained. The molecularity can be simply identified from the RDS step. Check how many molecules are present in RDS. If only one, like SN1, you'll call it as unimolecular. If both reactant, meaning substrate and nucleophile, both are present, like in SN2, you'll call it as molecularity of reaction is 2. Also, if you look at the concentration of substrate, nothing written, meaning substrate to the power 1, concentration of nucleophile to the power 1, meaning with respect to substrate it is first order, with respect to nucleophile it is first order. Overall, it is a second order reaction. So SN2 is bimolecular as well as it is second order reaction mechanism. That was about the important features of SN2, and now we are talking about energy profile diagram. Dear students, few minutes back we talked about what is energy profile diagram. So when we plot the energies of reactants and product along with intermediates against the progress of reaction, we get a curve. A curve obtained when we plot energies of reactant and product against the progress of reaction is what we call it as energy profile diagram. So if you try to recall reaction mechanism, we had starting point corresponding to substrate as well as nucleophile. Because it is concerted step, meaning attack of nucleophile and departure of leaving group taking place simultaneously. For attack of nucleophile to take place simultaneously, the substrate should be less sterically hindered. Hence, in case of SN1, sterically hindered substrate was favoring, but in case of SN2, least sterically hindered substrate will favor. So, at the starting point, we have got substrate as well as nucleophile. When nucleophile attacks at the carbon, slow step results in the formation of a temporary state where carbon is pentavalent called as transition state. And transition state is always a state of highest energy content. So the energy will increase and will reach to highest point, which is called as the transition state. So this is the transition state. Transition state being a state of highest energy content immediately leaves the leaving group and eventually gives you the product, which is your R connected to nucleophile. And because in nucleophilic substitution reaction, the energies of product is lesser than that of reactant, you will always find that the product being more stable, its energy is lesser than that of reactant. Now look, some important features. Well, we missed in case of SN1, we are just explaining that here. So this is the energy of, hold on guys. Reactant. This is the energy of transition state, or you can say activated complex. If you measure the difference in the energies between the reactant and the transition state, this is called as energy of activation, EA. So energy of activation is minimum amount of energy required for reactants to get converted to product, in simple words. Smaller the energy of activation, faster the transition state can be attained and faster the product can be obtained. Meaning lesser the EA, lesser the energy of activation, faster will be the rate of reactions. Hence all the factors which helps decreasing the energy of activation, meaning in other words, all those factors which stabilize the transition state and decrease the energies will always enhances the rate of reaction. So we are going to see few example in terms of typical substrate in the later part of SN2 itself. Now what we are doing, we are finding out energy difference between the energy of product and the reactant, guys. So if you just see the difference here and the difference between the reactant and product, this is your enthalpy of reaction delta H. So you can see because energy of reactant is lesser than that of product, this value is going to be negative. That indicates reaction is exothermic in nature. The similar term or the same term rather can be applicable for SN1 as well, which we missed. It's just that we had two humps there. So we'll be having energy of activation 1 and energy of activation 2 as well. Once we have learned characteristics of SN2, just like in SN1, we also learn the factors affecting the rate of SN2. So factors affecting the rate of SN2. The first one is substrate. Well guys, I have told you, whenever you talk about factors, you should always think about the key feature. What was the key feature of SN2? Concerted step. Meaning simultaneous attack of nucleophile, simultaneous departure of leaving group. For this to takes place, your substrate should be lesser sterically hindered. Meaning, now let's say I have got methyl halide compared with primary alkyl halide. That's primary alkyl halide because halogen is connected to carbon, which is primary. It is directly connected to only one carbon. Compared with secondary alkyl halide, compared with tertiary alkyl halide. Okay, now if you see here, primary alkyl halide is the one where carbon carrying leaving group is least sterically hindered. In case of primary, once one hydrogen is substituted by one alkyl, there will be little steric hindrance. So the approach of nucleophile will be relatively difficult in primary as compared to methyl. In secondary, there are two such alkyl group present at the carbon carrying leaving group. So this is the sterically hindered carbon with two bigger groups. So approach of nucleophile will be even difficult. And in tertiary, there are three alkyl group present. So this carbon is that sterically hindered that it can never undergo SN2 type of reaction mechanism. Hence, tertiary substrate are non-reactive towards SN2. So order of reactivity is methyl halide most reactive, then primary, and then secondary. So as the number of alkyl group at the carbon carrying leaving group increases, rate of SN2 decreases. Second factor, nature of nucleophile. Again, because we are talking about SN2, which is the concerted step, we want simultaneous attack of nucleophile and departure of leaving group. So we want a nucleophile to be strong enough to attack at the deficient carbon. So strong nucleophile meaning anionic nucleophile. So we can say stronger nucleophile that is anionic nucleophile favors SN2 because we have studied that anionic nucleophiles are stronger than that of neutral. So anionic nucleophile which is stronger nucleophile will always favor SN2. Nature of solvent. Well guys, look, As we know that we need a stronger nucleophile. Stronger nucleophile meaning what kind of nucleophile? Anionic. Imagine if you use polar protic solvent. So when we studied in class number 1, anionic species gets solvated by the polar protic solvent. If such anionic species will be solvated by a polar protic solvent, those will be captured or caged. Hence, they will not be able to freely attack at the deficient carbon. But in case of SN2, the requirement is that we need an anionic nucleophile which can attack at the deficient carbon faster. So we cannot use polar protic solvent, otherwise polar protic solvent will decrease the nucleophilicity of nucleophile. Hence, for SN2 to be favored, we need polar aprotic solvent. So generally DMSO, DMF, DMA, acetone, this kind of solvent favors SN2 reaction mechanism. So everyone, polar aprotic solvents favors SN2 reaction mechanism. Alright, so these are some of the important factors affecting the rate of SN2. And now we are talking about typical substrate favoring SN2. Look, so far when we talked about nature of substrate, we only consider those orthodox alkyl halide, primary, secondary and methyl halide. Other than that, there exists some more substrate which are even more reactive than this normal alkyl halide. One of that is your allyl halide. Well, few minutes back we have considered all of them in SN1. They are still applicable in SN2 as well. Allyl halide are also favorable towards SN2. How come? Let's try and understand. Look, so we have got allylic carbon to which halogen is connected. X being more electronegative, carbon will acquire delta plus charge. So nucleophile is all set to attack at this deficient carbon. Now, how is this nucleophilic substitution faster than even methyl halide? Let's understand that. Firstly, at this carbon, other than 2 hydrogen, the remaining group is a vinylic group, right? CH2 double bond CH is vinyl, and this is allylic carbon. Now, because this carbon is sp2 hybridized carbon, which is planar, so it's a flat molecule which is not going to create steric hindrance. So there is no steric hindrance at the carbon carrying living group. First favorable factor. Second, because this carbon is sp2, which is more electronegative than sp3 carbon, it will also withdraw some electron pair towards itself, making this carbon relatively more deficient than if there would have been sp3 hybridized carbon. More deficient the carbon, faster the attack of nucleophile. And third, the most important reason, when nucleophile attacks at the carbon in the concerted state, the transition state that we have got where carbon halogen bond is in a process of breaking, nucleophile carbon bond is in a process of making, there is a delta plus charge. Now this is the transition state. Because at this partial deficient charge, there is partial delocalization of pi electron cloud. I am saying partial delocalization, meaning this pi electron cloud is stabilizing the positive charge. See, this is electron density that is getting partially delocalized towards delta plus, which makes this charge dispersal to take place. If positive charge is being decreased to some extent, I can say the stability of this transition state is increased. Stability increase meaning energy decrease. So in the energy profile diagram, when the stability of transition state increases, meaning its energy decreases, so energy of activation become lesser. Lesser the energy of activation, faster we can achieve transition state. Hence the rate of formation of product will also be faster. So you can see more or less these three factors collectively tells us that why allyl halide are faster reactive towards SN2 than the normal alkyl halide. Which three factor? I repeat again. First of all, this is sp2 hybridized carbon, which means this is the planar, so no steric hindrance. sp2 carbon being more electronegative makes carbon deficient, so attack of nucleophile is faster. And more contributing reason, At the transition state, the deficiency at the carbon is partially being stabilized by the partial delocalization, which decreases the energy of transition state and makes it relatively more stable. So energy of activation decreases and the product can be obtained faster. Same thing happens here. Delta plus charge at the benzylic carbon because of electronegativity of halogen when nucleophile approaches. In the transition state, again sp2 hybridized carbon of the phenyl will bring delta plus here, so the nucleophilic attack is faster. Once this delta plus charge is developed, the partial delocalization will stabilize the transition state. Energy will decrease. If energy of activation is lesser, the faster rate of reaction would be. Now we have got alkoxy group at the carbon carrying leaving group. So again, nucleophile attack at this deficient carbon. The transition state which is formed, first of all, O is more electronegative, developing delta plus to a greater extent, so nucleophilic attack will be faster. Once the carbocation is formed, the partial delocalization of lone pair, and delocalization of lone pair is far better than that of pi bond. So the transition state is stabilized here in a better manner than in case of pi bond. So this is the transition state which is stable. So energy of activation will be lesser and the rate of SN2 will be faster. Now, allyl halide are more reactive than alkyl. Benzyl halide are more reactive than allyl. Alkoxy group at the carbon carrying leaving group are even more reactive than both allyl and benzyl. And having electron withdrawing group such as carbonyl carbon at the carbon carrying leaving group is fastest among all. So why it is so that presence of carbonyl carbon at the carbon carrying leaving group increases the rate of the SN2 type of reaction? Well, the only reason that we can state by looking at the structure here is carbonyl carbon atom is strong electron withdrawing group. Because of strong electron withdrawing group, it withdraws the electron density of the carbon carrying leaving group towards itself, which makes the carbon sufficiently electron deficient, and more deficient the carbon is, faster the attack of nucleophile. So presence of electron withdrawing group makes the carbon carrying leaving group more deficient the carbon carrying leaving group, faster is the attack of nucleophile on it, hence the rate of SN2 reaction will also be faster. So guys, other than alkyl halide, these are 4 substrate which are more reactive towards SN2. Allyl halide, benzyl halide, alkoxy group at the carbon carrying leaving group, and the fourth one is carbonyl carbon at the carbon carrying leaving group. And now finally, the substrate which are non-reactive towards SN2 are vinyl halide and phenyl halide. Also you can have a bridgehead carbon of bicyclic compound carrying leaving group will also be inert. Why? Well guys, firstly we want nucleophile to attack at the carbon carrying leaving group, right? See here, in vinyl halide, because halogen carrying lone pair are in conjugation with the pi bond, if this lone pair delocalizes here, then we will get a formation of partial pi bond character. So if I draw, let's say a resonance hybrid, I'm directly writing resonance hybrid here. So you will see there will be development of partial pi bond character. So delta minus here. I'm drawing hybrid straight away, okay? I'm not writing the resonating structure. Delta minus here and delta plus charge here. So due to lone pair being in conjugation with the pi bond of vinyl group here, there will be a partial pi bond character develop. Development of partial pi bond character decreases the bond length. Decrease in the bond length will increase the bond strength. If bond strength increases, carbon halogen bond cannot be broken that easily. So the leaving group will not be in a position to leave. So SN2 reaction won't take place, because we always want leaving group to be good leaving group for any kind of reaction to take place. Also, if there is a partial pi bond character developed, then that will become electron rich part of the molecule. And when nucleophile will approach at this deficient carbon, nucleophile themselves being electron rich, they will be kind of repelled by the presence of partial pi bond. Hence, the approach of nucleophile won't be convenient at the carbon carrying leaving group. Same thing will happen in case of phenyl halide, but to even greater extent. Because now lone pair are not just in conjugation with pi bond, there is further conjugation of 2 more pi bond as well. So to this lone pair, there is extended conjugation, pi alternate pi alternate pi. So development of pi bond character will be even more. More the pi bond character, shorter the bond length. Shorter the bond length, stronger the bond is. Hence poorer would be the leaving group, which will not favor SN2. Hence, due to development of partial pi bond character between halogen and the carbon atom of vinylic carbon and phenylic carbon, SN2 type of reaction won't take place in case of the vinyl and phenyl halide. However, let me tell you, if you introduce strong electron withdrawing group at ortho or para position of this phenyl halide, then this substrate can undergo nucleophilic substitution reaction. So you need either presence of EWG or maybe some strong, or you can say drastic conditions are required for such nucleophilic substitution reaction to take place. One such reaction you come across in the chapter of phenol called as Dauch process, where you take aryl halide, you treat that with aqueous NaOH at high temperature and pressure, and you manage to carry out nucleophilic substitution, but those are not the normal condition. You need a drastic condition for such substitutions to take place. As of now, we will say if those conditions are not maintained, then vinyl halide and phenyl halide will be inert towards SN2. So guys, that was all about typical substrate for SN2, and this finishes our SN2 reaction mechanism as well. So dear students, we studied SN1 and SN2 reaction mechanism in detail. Of course, we are going to study some examples, some questions on this part in the later part of this session. But as of now, we'll have to learn one more important reaction mechanism, that is neighboring group participation. Guys, I'm going to buy a few seconds from you all. Until then, you guys can go through this introduction so that it will become easier for you all to learn. Go through this. I'll quickly resume the neighboring group participation. Alright everyone, so the next reaction mechanism that we'll have to learn is neighboring group participation. We commonly abbreviate it as NGP. Okay guys, now this kind of questions you will see from NGP. You can expect questions only in examination like JEE. You won't really have such questions in NEET, very rarely, almost they won't ask any question, but JEE Advanced once has asked question from this NGP, and in boards for sure you won't have any questions. All right, so exclusively for JEE you can say, well, what neighboring group participation says, if you see the name of this reaction, neighboring group participation, let's say if you have got some primary alkyl halide which is expected to undergo nucleophilic substitution, that is SN2. Well, we have studied that for SN2 the order of reactivity of substrate is methyl halide the most, then second best is primary alkyl halide. So if I've got primary alkyl halide and if I'm expecting that to undergo nucleophilic substitution, of course we expect it to undergo SN2 quite faster. But in the same substrate, if there are some typical type of atoms or a group of atoms present, then due to presence of such groups will bring out the nucleophilic substitution reaction at tremendously higher rate than just a normal alkyl halide. And that tremendous higher rate of such primary alkyl halide would be due to presence of those atoms. Those atoms or a group of atoms participate in SN2 reaction mechanism and enhances the rate of such SN2 reaction unexpectedly. Hence we say, try and understand what I'm trying to say here. A number of nucleophilic substitution reactions are known which occurs with unexpectedly greater rate of a reaction. In this reaction usually there is an atom or a group of atom, an atom or a group of atom with unshared electron pair at beta position to the leaving group or even farther than that. So carbon carrying leaving group is alpha, next to that is beta. So at that position you might see there is some heteroatom like oxygen or sulfur present carrying lone pair or even nitrogen. So due to participation of some atom, such atoms, it displaces the leaving group so as to produce 3, 4, 5 or 6 membered cyclic intermediate, followed by the attack of the nucleophile that would be given in the reaction, and the SN2 reaction will take place. So usually this reaction proceeds with retention of configuration at a chiral carbon, an important feature. Guys, as of now we are just getting introduced. When we'll see the actual reaction mechanism, we will understand what exactly they are trying to say. The groups which behaves as a neighboring groups are, you can have sulfide group, ester group, carboxylate, ethers, thioethers, amine spinning nitrogen, or even halogen atom. Well, whatever we have said, to understand that, let me just take one example. Look, base catalyzed hydrolysis of PHS CH2CH2Cl. Well, carbon carrying leaving group is alpha, next to that is beta. So at beta position you have got heteroatom carrying lone pair. This substrate and look at this substrate. The only difference you see here is instead of phenyl and S, you just have got methyl. So even this is primary alkyl halide. So we expect such primary alkyl halide to undergo SN2 reaction anyways faster. But at this beta carbon, if you attach a heteroatom carrying lone pair, this is that neighboring group we are talking about, then the rate of this reaction is 600 times faster than the normal alkyl halide. You understand, the rate is become so faster, 600 times faster, because of presence of such neighboring group. Hence hydrolysis of such molecule will be as a result of the neighboring group participation. How? Let us try and understand. So to understand, I'm writing the reaction. So this is our substrate. Okay, so the reaction can be written like this. Let's say we have PHS connected to CH2. Well, I'm writing this substrate such that it is convenient for us to understand the reaction, and connected to chlorine. Now chlorine being more electronegative and connected to carbon will carry delta minus, carbon will carry delta plus charge. Okay, now look, if I allow this substrate to react with base catalyzed, so let's say the reaction is in presence of aqueous KOH. So aqueous KOH meaning this is an alkali which will dissociate to give you K plus and OH minus. So what we expect, OH minus is strong nucleophile, anionic nucleophile. Substrate is primary alkyl halide. So less sterically hindered substrate and stronger nucleophile, we expect a normal SN2 reaction to take place, which will substitute chlorine with OH and you get your corresponding product. However, reaction won't take place like that. How reaction takes place is, before OH minus could attack at this deficient carbon, the sulfur at the beta position carrying lone pair attacks at this deficient carbon and the chlorine leaves. So see, reaction is taking place within a molecule. This is kind of intramolecular nucleophilic substitution. Sulfur atom carrying lone pair is nucleophile, which is substituting the existing nucleophile. So reaction is taking place within a molecule. Now because the neighboring group is participating here, which is going to enhance the rate of reaction, I'm going to call it NGP, neighboring group participation. So as of now, what happened? NGP took place. And what we got? We got an intermediate. So pH S, one lone pair is intact, CH2 and CH2, right everyone? Where sulfur will carry positive charge. So we got a cyclic intermediate. So that's what we mentioned in the introduction. The neighboring group participates to form the cyclic intermediate of 3, 4, 5 or 6 member ring. Once you get the cyclic intermediate, now the nucleophile is all set to attack. Now look, this OH minus can either attack at this deficient carbon. Why is this deficient? Because this is connected to more electronegative atom. If attack takes place here, this bond will break. Or this nucleophile can also attack at this deficient carbon. If attack takes place here, this bond will break. But wherever attack takes place, because both carbons being equivalent, the product obtained is going to be identical, because these two carbons are equivalent. So you consider any of that. Suppose if I consider OH attacking here, so this bond is breaking. We are assuming this is taking place. Okay. So OH attack, this bond broke. See what I got. pH, sulfur, one lone pair was there. Now this will also come. So two lone pair intact. Bonded to CH2. Bonded to CH2. Carrying OH. Right everyone? So now you see the product. You have got OH here in place of Cl. So this is a nucleophilic substitution only. But this reaction has taken place 600 times faster than if there wouldn't have been this sulfur over here. So the role of sulfur is very crucial. That itself is participating in the nucleophilic substitution reaction to form a cyclic intermediate and then giving you the corresponding product. Now some important feature that we have to understand here. Everyone, firstly, the neighboring group and the carbon carrying leaving group, meaning the leaving group and the neighboring group should be anti to each other. So the perfect stereochemistry for the attack of neighboring group at the carbon carrying leaving group will be when the leaving group and the neighboring group who is going to participate are anti to each other. Because they are anti, when the sulfur attacks, since the attack is from the back side, the first attack will result in the formation of inversion. So the cyclic intermediate that we get will be inversion. Once you get this inversion, then the OH is again attacking. The attack of OH will again carry out one more inversion. So because inversion is taking place twice, the product will be with retention of configuration. Hence, second important feature, the product of neighboring group participation will always be with the retention of configuration. Right everyone? So here, this is one of the example. Let me just take few more example where we may have a non-equivalent carbon. So how do we decide major minor? Look at this. Now in this case, they are asking us to carry out reaction with, let's say again, aqueous KOH. All right. So that's a carbon carrying leaving group. So we have got delta plus here, delta minus here. Lone pair of nitrogen attacked here, bromine left. So we have got a nitrogen carrying 2-methyl. Well, CH2 and the carbon where there was bromine. So here there was bromine. So this is the new bond. And we have got methyl here. And that's a positive charge. Right everyone? See, nitrogen is connected to CH2. Nitrogen connected to CH2. CH2 was connected to carbon where there was bromine. So at this carbon, the new bond has formed carrying methyl. Now, naturally, because nitrogen is carrying positive charge here, either this bond will break towards nitrogen or this bond will break. So what I'm trying to tell you is, now if we have got OH minus ion to act like a nucleophile, this OH minus ion can either attack at this carbon so that this bond will break, or they can attack at this carbon so that this bond will break. So this carbon, you can see, is relatively less substituted because this is two valencies are satisfied by nitrogen and carbon, remaining two are just hydrogen. So this is less sterically hindered. But this carbon is connected to carbon, then nitrogen and methyl. So this is more sterically hindered carbon. This is a less sterically hindered. Less sterically hindered. If this is less sterically hindered, the nucleophile will prefer to attack at less sterically hindered. Hence, this is going to be a major product. So let's call it as path A product. And up there is path B product. So if path A is taking place, what is the product obtained? If path A takes place, this bond would be broken. So we'll get nitrogen with the lone pair connected to carbon carrying methyl and OH. So the product is N with 2-methyl. Now got a lone pair back here. This is connected to a carbon carrying methyl, connected to CH2 with OH. Okay. OH, when attacking at this carbon via path B, this bond would be broken. So the product would be N with 2-methyl. Attack is taking place over here. So we have got CH2, CH2, methyl with OH. Alright everyone. So this is path A product. This is path B, minor. And because path A product is taking place at the less sterically hindered carbon, this is path A product, which is the major one. Alright guys, so this is one of the example of, you can say, NGP. One more cyclic example you can see here. So there is some cyclic molecule, carbon carrying leaving group here is a chlorine. So we have got delta plus, chlorine carrying delta minus, and chlorine is pointing below the plane, sulfur is above the plane. So definitely this is anti to the leaving group. So the lone pair of sulfur can attack here and chlorine will leave. So as a result of which, the intermediate that we would be getting is okay. So we have got H here. Now see, because sulfur is attacking from above the plane, this H bond will flip down, right? Because what happens is inversion, right? At the carbon where backside attack taking place, inversion takes place, so H will flip down. And here a sulfur has formed new bond with a methyl group. And the positive charge carrying one lone pair on it. Now guys, when KOH will attack, okay, I'll do it this way. Now when KOH, meaning OH minus, is attacking, attack of OH minus can take place either at this carbon or at this carbon. Now both are equally probable. But the product obtained are going to be a two different products. So let's understand that. If OH attacks here, let's call this is path A, this is path B. So this is path A product, this is path B product. Path A takes place, this bond will break here. OH is attacking from below the plane, so H will flip up because there are two backside attack taking place, right? So first backside attack here, you got inversion, again backside attack, again inversion, meaning product will be overall retention, you can say. So OH attacked here, so H went up. This is the incoming OH. So this bond broke. SCH2 is above the plane. And H as it is. Plus, if attack via path B is taking place, so OH is attacking here, this H will flip up and this bond is going to break. If path B attack taking place, this bond has to break. So SCH2 will be to this left hand side carbon above the plane. OH attacked here. So OH, hold on guys, let me change the color. Yes, OH is below the plane, right? H will be flipped up. SCH3 above the plane here. And this H is pointing downward. So we got these two products. Now, if you look at this is a chiral carbon, even this is a chiral carbon atom. But there is no mirror plane of symmetry, so this is optically active compound. Even this is optically active compound, and both are the mirror images of each other. So this is a pair of optically active isomer of a same compound which are related to each other as a mirror images, so they are enantiomers. Because both enantiomers are obtained by the equally probable attack, I can say that these two will be obtained in equimolar amount. So equimolar mixture of optically active isomer of the same compound is what you call it as racemic mixture. So this product obtained will be a racemic mixture. Hence the process can be referred as racemization. So guys, we studied several neighboring group participation. Let me just put some important features of NGP. So in a rate determining step, you will see only one molecule will be involved, because within a substrate there is internal nucleophile present. So NGP is the first order reaction. The rate is proportional only to the concentration of substrate, meaning reactant. Substrate rather, you must say, okay, not the nucleophile. So preferably we should call it as substrate only. Substrate only. NGP is intramolecular nucleophilic substitution. Of course, we saw that internal neighboring group which act like a nucleophile and attack at the deficient carbon before the external nucleophile could attack. So it is intramolecular. For NGP to take place, nucleophile, okay, this has to be nucleophile, and the leaving group must be anti to each other. Yes, we have seen. That's why the first attack is backside. Second one is also inversion. So overall, you will see there is a results in the formation of retention of configuration of the product. So everyone, that was all about neighboring group participation, and with this we have finished the first type of reaction mechanism of alkyl halides, that is nucleophilic substitution reaction. Now just to conclude this nucleophilic substitutions, we are going to do few questions here, guys. The first one for you, while again there could be a question from the session 1 as well, like you can see here. In the given reaction, ethyl halide treated with CH3SNA, CH3SNA meaning CH3S minus and Na plus. So this is anionic nucleophile. This is primary alkyl halide, which means they are talking about SN2 reaction mechanism. The fastest rate of reaction occurs when the value of X is, what is X? X is a leaving group. So they are asking, out of these 4 leaving group, which leaving group should we take here so that the rate of SN2 will be faster? Well, when we studied SN2 reaction mechanism, one of the factor which we saw was a leaving group, and I told you, universally, whether you are learning any substitution or any elimination reaction, the rate of SN2 will be faster if you have got a better leaving group. So for a better leaving group, what we have learned? Poor bases are good leaving group. Poor bases are good leaving group. I'll write it down once again. poor bases are good leaving group. So what you'll have to do, you'll have to convert all of them into their acids. Check whichever acid is strong acid, its corresponding conjugate base is going to be a poor base. So if I talk about the first one, OH is the leaving group which is a conjugate base of water. You just have to add H. If you add H here, this is going to be HF. If I add H here, CF3COH, by the way, this is nothing but I added H here, OH, then we have got C double bond O. So this CO is C double bond O carrying CF3. Yes, this is trifluoroacetic acid. And here, if you add H here, ideally there should have been bond here. So this is OH, C double bond O and CH3. So this is acetic acid. If you see here, the strongest among all this acid is this. And how do we know this is strongest acid? Well, one thing you need to know the pK value. But if you don't know the pKa value, lesser the pK, stronger the acid. But suppose if we don't know that, then how do we check that? Well, compound is acidic when the conjugate base is stable. So if I remove H plus from here, the conjugate base O minus, this negative charge is in conjugation with pi bond. Also, 3-fluorine will show strong electron withdrawing ability because it is strong EWG. Because it is strong EWG, it will withdraw the negative charge, which you call it as dispersal of charge will be more. More the dispersal of a charge, more stable will be this anion. More stable the anion, stronger the corresponding acid. So because this is strong acid, its conjugate base is poor and poor bases are good leaving group. So because this is the best leaving group will let nucleophile to attack faster and itself will leave faster. So which means because of the better leaving group, the rate of reaction will be faster when the value of X is this corresponding trifluoroacetate ions. Alright everyone, excellent. Next question. The rate of SN1 reaction is fastest with. Well guys, I've told you whenever you solve questions on this reaction mechanism, you should think of few important points. Like key feature is very important point that will always help you to solve question on this. So what is the key feature of SN1? Yes, it results in the formation of carbocation. So when you talk about SN1, you should always think of carbocation formation. So carbocation formation will be faster when the carbocation form is stable. More stable the carbocation, faster will be its formation. So when you look at this A, B, C and D, you have to look at the carbon carrying leaving group, and if the leaving group is leaving, which carbocation form will be more stable. So straight away in option A, imaginary bromine leaves, then the carbocation formed here will be stabilized by the phenyl ring to the left as well as phenyl ring which is represented to the right. So this carbocation can be stabilized by both this phenyl ring. Such carbocation stabilization is not taking place anywhere else. Here in B, if you form a carbocation here, this will be stabilized by resonance, but this will be only stabilized by plus I. So resonance stabilizes better in A. In case of option C, after departure of leaving group, the carbocation can only be stabilized by plus I. And here, after departure of Br, the carbocation is stabilized by this phenyl ring. But here this carbocation is stabilized from both sides by the phenyl, which makes it more stable. More stable the carbocation, faster will be the rate of SN1. Hence option A is the appropriate option. Next question everyone. Well, very interesting. When the concentration of alkyl halide is tripled and the concentration of OH minus is reduced to half, the rate of SN2 reaction increases by. Well, if you see here, the question that they are talking about is about SN2. For SN2 rate is equal to K into molar concentration of substrate right? Hold on, guys. Okay, so rate is equal to K into molar concentration of substrate into molar concentration of nucleophile. This is what we have studied. Now what they're asking, when the concentration of alkyl halide is tripled, so whatever is rate, you have tripled it, and the concentration of OH is reduced to half. See, because rate is proportional to molar concentration of substrate as well as nucleophile, by altering the concentration of either of this, the rate will also be altered. Depending upon how much are you increasing or decreasing, the rate will also change accordingly. So what are we doing? We are tripling the concentration of substrate and we are reducing the concentration to half, meaning to half. So overall, if you see, the rate will increase how much? 1.5 times. Isn't it? So if the concentration of alkyl halide is tripled but the concentration of OH is reduced to half, the rate of SN2 reaction increases 1.5 times of the earlier rate. So guys, those were 3 important questions, and the last one on your screen here. SN1 reaction is favored by, well, we have seen that SN1 reaction, first option is about the solvents. SN1 reaction is known as hydrolysis, meaning you need polar solvent to help the dissociation of carbon halogen bond. So non-polar solvent is not what we use. Option A ruled out. Bulky group on the carbon attached to the halogen atom. Yes, we have studied that as the number of alkyl groups on the carbon carrying halogen increases, the rate of SN1 increases, right? Because as the number of alkyl group at the carbon carrying leaving group will increase, the corresponding carbocation form will be more stable. So you want alkyl halide which is sterically hindered. So bulky groups on the carbon carrying carbon atom attached to the halogen atom is the favorable condition for SN1. Hence option B will favor the SN1 reaction. So guys, that was all about few important questions from the nucleophilic substitution reactions. And today we have covered the most important mechanism, including SN1 as well as SN2, and then we also saw neighboring group participation. So guys, I'm hoping that you guys are understanding what we are learning here. I request you all to please keep solving more and more questions. Do not miss the class, and if you do, please make sure that you are watching the replay. So that is it from our today's class. Thank you so much for attending this session, and we'll stop here. But I'll see you soon. Thank you so much, everyone. Take care.